I am deeply honored and grateful to the Inamori Foundation for awarding me a Kyoto Prize in Basic Sciences and for the opportunity to present these reflections on my life and work. Although I was born in Boston, USA in 1932, also Showa 7, Japanese, it was in New York City that I grew up and formed my view of the world. My family was middle class, but New York City offered a good quality, free public school education, the Bronx High School of Science. I discovered that I like to build things and to participate in amateur or ham radio construction. What I was most proud of was learning the Morse code well enough to pass the examination for a license to transmit W2ZHS and connect with operators across the globe. These early efforts, in which my older cousin was influential, was leading me, I thought, to a career in electrical engineering. When I was 17 years old, my family moved back to Boston, and I was privileged with encouragement from the eminent physicist Victor Weisskopf to go to the Massachusetts Institute of Technology, known as MIT. Shortly after entering MIT in 1949, my outlook changed during my very first physics course. Matthew Sands, who co-authored the influential Feynman Lectures, showed me the intellectual beauty of Newton's physics. At first, I had difficulty grasping the contents because my high school classes had not really prepared me for the deep understanding that a theorem such as Newton's equation, force F equals mass m times acceleration a, means exactly what it says and nothing more or less. In order to find A, one must first find the magnitudes of the force and the mass in different applications. It required half the duration of the course, plus Matthew Sands' patient help, but I finally understood the significance of the equation, and my career in science was off to a good start. Newton's contemporaries must have had similar difficulties. Thus, I gave up engineering and changed to a pure physics course for the rest of my undergraduate studies. As an undergraduate at MIT, I was lucky to get a part-time job in the group working on one of the very first linear particle accelerators known as LINAC, and this was a 17-volt electron volt machine, which was big then but infinitesimal now, and was built by two of the nicest and most encouraging people I ever met, Isaac or Ying Halpern and Peter Demos. Unlike the science of chemistry, physics was a subject not very well known to the general public in 1949. And my father thought that my sudden career decision into physics would lead me into poverty. It turned out otherwise. And I was lucky to ride the post-war wave of government funding of science with a decent standard of living. Mathematics played a role in my studies, but not a big one. I was most fortunate to learn advanced linear algebra at MIT from Isidor Singer of Atiyah-Singer index theorem fame, who became a good friend. After graduating from MIT, I wanted to get out of my cocoon and see something of the world. Up to that point in time, I had traveled rather little, apart from visits to large American cities. Professor Weisskopf, with whom I did my senior thesis on relativity theory, thought that the Department of Mathematical Physics at Birmingham University in England, with Professor Rudolph Piles and lecturers Sam Edwards and Jerry Brown, was one of the best places in Europe to do theoretical physics. And they spoke English, which is important for me since I had no exposure to any other language. John Bell, who went on to invent extremely important inequalities in quantum information theory, was a fellow student. During those years, I did manage to fulfill my quest to visit most of Europe. After 3 years at Birmingham, and with an uninspired PhD thesis of little value, I graduated in 1956 with a PhD degree. My next stop was Kyoto. Why Kyoto? My uncle, who owned an art bookstore in Boston that specialized in Japanese art, inspired in me a deep interest in ukiyo-e prints. In Birmingham, I was lucky to share an office with a Japanese nuclear physicist named Yoshida Shiro. I was asked to help him improve his English, and he reciprocated by teaching me elementary Japanese without any kanji. I spoke as an illiterate. Nevertheless, the U.S. Fulbright program gave me a one-year fellowship to Kyoto University's Yukawa Institute for Theoretical Physics. That year was formative for me culturally and scientifically. Up to that point, I wondered if I would ever be able to contribute anything of value to science. In Kyoto, I just did that, or so I felt. After Kyoto, it took another 4 years to do so again. In the Yukawa Institute in Kyoto, I met a brilliant young Japanese physicist, Yamazaki Kazuo, with whom I formed a close collaborative association. Together, we worked on a challenging problem in physics, the Polaron problem of an electron trapped inside a crystal. It was a popular topic at the time, and we decided that we were going to go beyond intuitively motivated calculations and try to calculate the Polaron's lowest energy state in a mathematically rigorous manner. We were able to prove that the Polaron energy was actually finite. In other words, that a lowest energy exists. Other physicists, like Feynman, took this for granted, despite the fact that similar-looking models failed to have a finite lowest energy. In this way, we opened a new chapter in our lives as well as in the theory of the Polaron. Thanks to my stay in Kyoto, I was now convinced that I could actually do research. 2 years later, I met Richard Feynman himself at Cornell University, and he asked me about my interests. When I told him proudly what I had done in Kyoto, his rather aggressive reply was that real physicists don't do that sort of thing. In his opinion, I was wasting my time. As a young beginner, that negative encounter set my sail ever more firmly toward mathematical physics and its importance to physics. From Kyoto, I went for a year to the University of Illinois, followed by 2 years at Cornell University, under the famous Nobel Prize winner, Professor Hans Bethe, who was the one who explained the nuclear reactions that make the sun shine. Alas, these 3 years produced nothing and made me uncertain again about my future as a mathematical physicist. But it did lead me to a problem that occupied me for the rest of my life, namely the quantum mechanics of a certain gas of atoms called a Bose gas, especially its coldest or lowest energy state. Thus, I spent 2 years at one of the best institutions of its kind, Cornell, with one of the world's greatest physicists, Bethe, and came away in 1960 with nothing to show for it except for a problem to continue thinking about. It laid in my mind for 36 years until Jakob Ingvason and I solved this boson problem in 1996, and thereby started the current interest in Bose gases among mathematical physicists. From Cornell, I moved to the IBM Computer Research Center in Yorktown Heights, which is in New York, which had just opened that year. in 1960. It was my first permanent position, although I stayed with IBM for only 3 years. I was lucky to find two colleagues my age, Ted Schultz and Daniel Mattis. We three physicists felt that we wanted to prove some accepted theories by thinking mathematically. This interest of ours was then outside the realm of research in any other industrial research laboratory, and we were thankful that IBM gave us this freedom. In general, 1960 to 1970 was a wonderful decade for physics research around the world. Several theorems of importance to physics came from that period. One was the Lieb-Mattis theorem that magnetism never occurs in one dimension, meaning in a simple chain of atoms. Most theorists at the time, including Heisenberg, my old Birmingham PhD advisor Piles, and my Cornell mentor Bethe, thought the very opposite, namely that ferromagnetism always occurs and in one dimension, and it took some effort to convince colleagues that we were correct. Piles called it a surprise in theoretical physics. Mattis and I also developed theorems about Heisenberg spin models, which are still used today. In the second of those 3 years at IBM, I was on leave in Sierra Leone in West Africa to teach applied mathematics at the university in Freetown. There were many adventures of a social political kind, as well as a bout of malaria, but I also had time to think about science. It was there that I invented the model of Bose particles, or bosons, in one dimension, which I worked out later with Werner Liniger when I returned to IBM. This model is fundamental for understanding the quantum many-body problem, and it has been confirmed experimentally, even though our model is only a model for a chain of atoms. After 2 years at Yeshiva University in New York in 1966, I moved to Boston again to take a professorship at Northeastern University. There, Professor F.Y. Wu and I wrote the most cited ever paper in the journal Physical Review Letters about the exact solution of the one-dimensional Hubbard model. It still holds that citation record today. That is to say, it's the most cited ever paper in Physical Review Letters. I now turn my interest to ice. What does ice have to do with mathematics? One other important exact solution was made at Northeastern University, this time to the combinatorial problem of two-dimensional ice. The story goes back to the experimental result that the entropy of ordinary water ice at absolute zero temperature is not zero. This means that there is significant randomness in the arrangement of its oxygen and hydrogen atoms, which cannot be frozen out. There is still some sort of life left at absolute zero. The explanation came from the two-time Nobel Prize winner, the chemist Linus Pauling, who said that while the oxygen atoms are nicely arranged, the hydrogen atoms are not. One hydrogen atom lies between every pair of oxygens, but the hydrogen atom is closer to one or the other of the two oxygens, with the ice rule condition that each oxygen has two hydrogens close to it and two farther away. The entropy is the logarithm of the number of ways to make such an arrangement. The slide shows the two-dimensional version of the problem. The vertices represent an oxygen atom, and the lines show the way in which the hydrogen atom between two oxygen atoms is displaced. The ice rule requires that two arrows point into each oxygen and 2 point outward. Andrew Leonard observed that this counting problem is identical to the following coloring problem. How many ways can we color a tiling with squares, like a checkerboard, using 3 colors only, so that neighboring squares always have different colors? The answer that I found, when there are many, many squares, say n, is the following. The number of ways is the 3n over 2 power of the number 4/3 to the 3/2, which is 1.5396007. And this number, 4/3 to the 3/2, has been called Lieb's constant. The result gave birth to a whole subfield in combinatorics called the 6-vertex problem. A few months after its publication, there was an offer of a professorship in the MIT mathematics department, which I accepted. During the next few years, a high point was my work with Joel Leibowitz on the existence of the thermodynamic limit for Coulomb forces. This theorem, together with the Freeman-Dyson-Andrew Leonard proof of the energy lower bound for electrically charged particles, proved the stability of matter. Stability of matter is a fundamental problem which can be briefly stated as follows. Consider an atom, which can be pictured as a nucleus surrounded by electrons. This picture is crude but not wrong, and raises the fundamental question that troubled people around 1900. Why do electrons not fall into the nucleus? Quantum mechanics explains this nicely. Why then do atoms which appear to be as fragile as a spider's web not collapse into each other? Quantum mechanics comes to the rescue again, but the explanation is very complicated. Atoms can attract each other, but only very lightly, and they retain their identities. Unraveling this story took several decades of mathematical research, and I contributed to some of this. The solution to this problem required contributions from several people, including myself. This line of research is one of the most important examples of the contribution of mathematical physics to our understanding of physical reality. In 1973, Mary Beth Ruskay and I proved the strong subadditivity of quantum entropy, which lies at the base of some areas of quantum computer science and of physics. A different major result in the same year was my work with Barry Simon on Thomas family theory of atoms and molecules. This theory gives a simplified but quite useful picture of the structure of atoms without delving into the more complicated mathematics of quantum mechanics. It requires a heavy dose of mathematical analysis, however, and thus begins my period of pure functional analysis. Examples of my other work at this time period are the Braskamp-Lieb inequalities with the young physicist Hamjan Braskamp. These calculus inequalities relate integrals of products of functions to products of integrals of these same functions. I was surprised to find later that theoretical computer scientists often use these inequalities in their work. In 1975, I accepted an offer from Princeton University jointly in its mathematics and physics departments. In the same year, Walter Thierry of the University of Vienna, one of the world's most famous mathematical physicists, and I struck up a friendship and set to work to find an alternative proof of the Dyson-Leonard proof of stability of matter. That proof was rather complicated, and we felt there should be a simpler one, and we managed to succeed in this effort. Let me conclude by mentioning 3 other works done at Princeton. One is the Lieb-Oxford bound for atomic exchange correlation energy in quantum mechanics, which is the glue that binds atoms and molecules together. This is another result originating at Kyoto, because I had the idea for finding limits to this particular quantity during my second stay in Kyoto. My 1979 sabbatical leave at the Kyoto Research Institute for Mathematical Science, also known as RIMS. This was the last year also of the tramway or densha in Kyoto, and I was fortunate to see the very last densha. The bound I found in Kyoto was a weak one, however. A year later, with Stephen Oxford at Princeton University, we refined it enough to make it a bound closer to reality and thereby make it truly useful for computations. A second equally influential paper also had a touch of Japan. This is the AKLT model of electron spins, named after Ian Affleck, Tom Kennedy, and myself, and Tazaki Haruaki, who was a postdoctoral researcher with me in 1987. It proved an older conjecture in physics, which is that it is possible to have a gap between the ground state energy and all the other energies in a truly quantum system of particles. The last work that I will mention, and that I regard as one of my deepest, is the 1990 paper with Jakob Ingvarsson on the meaning of thermodynamic entropy. The true meaning is not about jiggling atoms and other models that date back to Boltzmann. Rather, it can be defined without any mention of temperature or cycles or models or chaos. In our view, entropy is simply a quantity whose increase defines the necessary and sufficient condition for any proposed process to take place. Its fundamental existence is guaranteed if certain simple axioms are satisfied. Many people like our point of view, but some others think it is irrelevant. Which reminds me of my experience of such an attitude from Feynman many years earlier. Even in the hard sciences, taste plays an important role, and people can disagree about the significance of any particular line of research. In this talk, I have touched on several areas of mathematics and of physics and the combination of the two. I have been fortunate to interact with many exceptional colleagues in several countries and to have received enough support and encouragement along the way to persist despite initial doubts. It is with humility that I thank the Inamori Foundation for awarding me a Kyoto Prize and for the opportunity to present these reflections on my life and work.
Elliott, thank you so much for your personal account of the journey you took, which resulted in your remarkable accomplishments. If you were here in an auditorium in San Diego, I am sure that the room would be full of applause, as it was a few months ago in Kyoto. Let me begin by going back to the beginning of your lecture. You said that it was shortwave radio and electronics that had got you interested in engineering as a youth. Why did you initially focus on engineering rather than drilling down deeper into where electromagnetism came from?
I didn't learn about electromagnetism in high school, and I didn't even know it existed. I only learned about it in my second year at MIT as a student.
So later on in life, your curiosity led you to deeply fundamental aspects of very practical things, like the stability of matter, as you talked about. How did this change in style come about?
Stability of matter was a topic that came very much later to me. It wasn't really a style change so much, but a question of intellectual maturity.
I see. So, so that intellectual maturity, I guess, from what you said, started with having your eyes opened by Matthew Sands to Newtonian mechanics, and this prompted you to shift from engineering to physics. But I guess a question I had, and maybe other viewers, to have been admitted to MIT in engineering, presumably you already must have known some rudimentary Newtonian mechanics.
No, as a matter of fact, I didn't learn anything about Newtonian mechanics in high school. And that high school, by the way, was Bronx High School of Science, which was supposed to be one of the best in the country. The only good courses there were mathematics and English, not physics and chemistry.
What was it in particular that inspired you about Sands's lectures?
Well, Sands' lectures were my first really serious introduction to science. His lectures were extremely clear and pedagogical. That's very important at the beginning. Sands was the co-author of the famous Feynman lectures, Sands and Layton, who wrote up the Feynman lectures.
Yes, you described that later on you met Victor Weisskopf, and he suggested for you to go to Birmingham, UK. One of the people in the audience wanted to ask the following. She asks, this is Tanya Sharpie, who's my colleague here at UCSD and in the Salk Institute. She says, you mentioned humble beginnings, but you also mentioned that Weisskopf helped you to be convinced to attend MIT. How did you meet him, and how did that happen?
Oh, that's a complicated story, but basically, my uncle owned a bookstore which was specialized in Japanese and other Oriental art, and there Weisskopf came, is also interested in this subject, and they met and they talked, and that's how I got to know Weisskopf through my uncle.
Right.
And Japanese art, and ukiyo-e, common interest in ukiyo-e.
I see. And then later, Victor Weisskopf suggested for you to go to Birmingham for your PhD. Why? What did
Actually, he didn't actually suggest that. It's a little bit more complicated than that. He suggested that I stay in the US for my PhD, but I was insisted on going abroad because I wanted to see the world. So he said, well, in that case, go to Birmingham. That's the best choice for you if you want to go to Europe.
What did he think you would learn that you would not learn at MIT or elsewhere in the US?
Oh, nothing whatsoever. So he was not advising me to go abroad. But if I'm going to go abroad and the only language that I know besides English is English, then
I see. Yeah. At that time, you touched on this a little bit. Rudolf Piles was the professor of mathematical physics in Birmingham, and he'd moved there after the war from Los Alamos.
much later.
Many of the students and early career scientists there later went on to become the intellectual leaders of physics and mathematical physics. And you mentioned John Bell. It must have been a unique time and place. Can you give us a flavor of what it was like to be a student there at that time?
Well, it was rather a little bit secluded. It was just took place in what the British call a Nissen hut, Quonset hut, we call it. And but lots of famous people came through, amazingly. And what did I learn that I couldn't learn in the U.S.? Nothing. I mean, it was a wonderful place, and there are wonderful places in the U.S. too.
What was the cultural environment like? Were there within the department? Did Piles entertain the students and so on?
Well, yes, especially his wife Eugenia. In fact, the students had to play the scissors game as an initiation. I think everybody knows that. And so it was that kind of atmosphere. It was very congenial and family-like and definitely not like being you were just a graduate student in a big university. Sort of a family. And then there was Jerry Brown, who was there, who had big influence on me, famous American physicist, who had a position there.
There's a question from the floor. Would you recommend striving for a deeply international academic journey, even if it means spending 2 or 3 more years in graduate school than you normally would? I think they're asking, that there's pros and cons of going overseas for your PhD. Actually, if you go to do a PhD in the UK, as you did, it's actually shorter than doing a PhD in the United States.
Yes.
But I think they're asking, does the experience of doing an international PhD, is that sufficiently broadening that it counteracts any inconveniences that there might be otherwise?
It depends on the person. Some people want to go straight for the PhD and move on. That's one kind of person. Another person wants to see the world and academically and culturally, which was what I wanted to do. So I was willing to spend extra time doing that. So it depends very much on the student. Unfortunately, as time went on and conditions became more constrained in the academic world, if you wasted too much time, you got sort of black marks.
Mhm.
And, so you have to be determined if you want to stray a little bit.
Right. I wanted to ask you, since you were there at the Pyle School at this very propitious time for mathematical physics, what do you attribute the incredible lasting influence and legacy of the Pyle School on science?
Well, what do I attribute? And it was not rigid. Everybody was sort of studying in his own way and developing their own interests. And at first, this is not a good thing because you don't fit in quite so nicely. But I was doing this at a time when the academic world was wide open and very flexible. How it is now, I am not so sure in this respect.
Right. Well, you worked with Sam Edwards as your advisor, and by your own words, you wrote a not very inspiring thesis. I want to ask you, how did you choose to be working with Sam? And then I'll ask you, I have a follow-up question for that after you've answered that question first. So how did you choose to be working with Sam?
I didn't choose him. I was assigned to him. That's how it worked. I first worked with Jerry Brown and even wrote a paper with Jerry Brown. So that's my first published paper. And so Sam came second, so to speak. But both of these people were big influences on me. And Piles recommended Sam because Sam was interested in functional integrals. And that was the mathematical frontier at the time in physics. So that was a good suggestion.
Mm-hmm. Did you feel at the time that your thesis was not inspiring to you?
Yeah, yes, I did. It was not what I would have done if I had known more, had a broader view of things.
How did you persist in science then if you felt that way? Is there advice that you can give to today's students and professors who might be in a similar situation? We've all, done PhD theses, and after we've done them, we may say, well, that wasn't so great. What are the ways to make the experience more meaningful and satisfying? And if one does feel like that, how should one motivate oneself to carry on?
Well, you have to be persistent and be prepared to chart your own course and take responsibility for it. But you also have to be prepared for the occasional failure.
Right. Well, so then you went to Kyoto for your postdoc. How did you sense a difference in scientific style? And you mentioned, by the way, in the talk, the Polaron. Could you say just a little bit more about what a Polaron is and what was the problem that really needed understanding and what was different about your approach?
Well, I got into the Polaron because of Yamazaki Kazuo in Kyoto, another young person starting out. And Feynman was working on the Polaron and it was therefore very popular at the time. The Polaron is an electron together with the distortion of the lattice produced by the electron through its electric charge. And and the approach that I was trying to take, as well as Yamazaki, with whom I worked, was to try to do what Feynman had done, but in a more rigorous manner.
So this was the time that you switched your style into more mathematical approaches to physics.
Exactly, yes.
What made you do that after working under Sam Edwards' supervision, where the style was the exact opposite?
Well, yes, it turned out that way, but at the time, when I was a student, there was no other choice for anybody working in anything mathematical at all. So working on functional integrals was regarded as being mathematical within the context of the Piles department.
Mm-hmm. Yeah, I see.
So that answers your question. It was what I had in that area to work with.
Probably other viewers have the same questions I'm going to ask you now. How did you learn the mathematics that enabled you to switch styles? Was it hard, and did you feel that your education prepared you for making this transition? And while you're at it, what advice do you have for other scientists who wish to pivot into new fields like that?
Well, I got into it on a need-to-know basis. I didn't approach it systematically, and which partly checks with the rest of my academic career at that time. How would I recommend it to other people? It depends very much on style, on your abilities and your style and what you want to do. There's no one recommendation I can offer.
Right. I mean, I'm going to just skip. I'm going to come back to the historical talk, but another question from the audience was, can you talk about your experience bridging math and physics at Princeton in particular? But of course, it could be earlier too. So I think they wanted to know a bit more about what it was like to bridge these two worlds.
Well, it really goes back much earlier than Princeton, or it goes back to about 1960, which was very shortly after I got my PhD, that I had a position at IBM with two other people with very similar interests. And I was not the only one in that boat. There were three of us, and we worked together very nicely. One was Ted Schultz, now deceased, and the other is Daniel Mathis, who's still with us.
I guess the question is, did you find, you personally were sort of doing work in both areas in mathematics and physics. How did you find, were mathematicians receptive to a physicist doing this? Were physicists receptive to a more mathematical style?
Well, generally, no, on both sides.
Right. Okay, that's what I expected. Let me go back to the
similar problems.
We'll come back to that, but let me go back to your historical narrative. So during the late 1950s, you worked at the University of Illinois at Urbana-Champaign. But you were there at a very fascinating time. You were there in 1957 or so when John Bardeen and his group were working on superconductivity and many body theory, and eventually that group won the Nobel Prize for their work. Did you have any contact with them when they were doing this work on solving the problem of superconductivity, at least decoupling?
No, absolutely no contact whatsoever.
So who did you interact with when you were at
Actually, nobody from the faculty in this postdoc position, in fact. But I did interact with a visiting German physicist, Heinz Koppe, and we wrote a paper together during this 1 year at Illinois. That was the main thing from my Illinois experience.
What was the paper about, and
the paper was about a simple model, not a very good model, but a simple model of the deuteron stripping reaction.
Amazing.
So you have a deuteron of a proton and a neutron, and along comes something and knocks off the neutron, and what does that look like? And
I see, yeah. So you're very separate from the condensed matter physics, even though later on you would move into condensed matter. And in fact, you started that journey back in 1960s when you moved to IBM. And at that time, for those who don't know, IBM and some other major corporations had very active fundamental research groups. You wrote an incredibly influential paper with Schultz and Mattis, who you mentioned, on the Onsager solution of the 2D Ising model. Could you? I'm going to ask you a question in many parts, but I'll take the question and then you can answer it as you wish. So for the audience who may not know, could you explain what the problem was and what was important about how Onsager solved it? And in particular, the pedagogical article you wrote was the thing that demystified his solution. I remember as a graduate student, that was one of the first papers I read, your paper on that. And after that, I could understand it. Why was his solution so obscure? And how did you understand it so well that you could reformulate it in much more elementary terms that an ordinary physicist could understand?
Well, we started from scratch, so to speak.
Mm-hmm.
The Onsager solution was regarded at that time, we're talking about 1960, in the same way that at one time Einstein's general theory of relativity was regarded as only 4 people in the universe could understand it, that sort of thing. It had that mystique about it.
Mm-hmm.
And we just, the 3 of us, Schultz, Mattis, and I, went at it just from a simple condensed matter point of view, and found our solution with bosons and fermions and usual things. Onsager never talked about that, but Onsager was a very special mathematical physicist, a great man. Did many things, but let's go on.
Yeah, well, when you reformulated the problem in a way that turned out to be incredibly influential later, but what did you find in reading his paper? What did you find to be the most interesting and original aspect of his solution?
Well, I don't read his paper very much. I mean, yes, I looked at it, of course, but not much really stayed with me. So we just de nouveau is.
I see. So knowing that it could be solved and knowing what the answer was, you then sort of tackled it afresh, as it were.
I think that's really the correct statement.
Mm-hmm.
To take any credit from Onsager,
Yeah, of course.
but we just had a different take on it.
Yeah. Did you anticipate the enormous influence that his work and your subsequent work, including the ice problem, would have on starting this field of exactly solved models and statistical mechanics?
No, not really, not at all. We thought that we were just doing something on the borderline of mathematics and physics, but it turned out to be of general interest to a lot of people.
So I want to ask. I've got a couple of questions coming in from the audience, which is great. I'm going to get to those in a minute. But I want to ask you. Well, actually, maybe I'll ask you this one now, because we just talked about your experience at IBM, where you had this wonderful collaboration that perhaps was the first hugely impactful scientific collaboration, and of course there were many others. What's your secret to an effective scientific collaboration?
Well, you have to find, it's not easy, but 2 people or more people who are at more or less at the same level of background knowledge, the same level of interest in fields of physics or mathematics, and willing to work together. That is, the psychology is compatible.
Mm-hmm.
This does not happen so easily. That's all I can say. We were just very lucky.
I see. Well, let me ask you a question, a different kind, not about what you worked on, but what you did not work on. So if you had asked me in the 1960s and 70s, all through the middle 1990s, what was the most urgent problem in physics where mathematics was needed to make sense of what physicists was doing, I would have said the problem of renormalization, how to make sense of the infinities in quantum field theory. So as far as I know, you didn't work on that problem, and I wondered if you could just say a little bit about why not?
Well, I was not terribly interested in that problem. And the first paper I ever wrote was on quantum electrodynamics, which touches on this subject. And I went through it and did a calculation, but I was not really turned on. I did it as a graduate student, and it turned out that I was more interested in the kinds of Ising model kinds of problems. So
I see.
that's the question of taste, really.
Yeah. Well, let me ask a question in a different way, a related question. This is from Julian Dukes, who asks, in mathematical physics, what would you say are the most important or widely used concepts to be exposed to?
Well, you should know some mathematics, apart from, of course, the usual physics education, which I won't dwell on. I think everybody knows that. But you should know some mathematics. You should know linear algebra, matrix theory, all this stuff very well. You should know some functional analysis, know how to deal with integrals, and which is lots of what's done has to do with manipulating integrals and knowing how to estimate integrals, that is, find uppers and lower bounds on the integrals without, of course, being able to evaluate them explicitly. This is an essential thing you have to have at your fingertips. Lots of tricks of the trade.
So you mentioned that you earlier on that you picked these things up on a need-to-know basis.
Yes.
And you just summarized some of the things that you think you would need to know. But if you don't know them, how do you know that you need to know them?
Well, that's the trick. You have
Okay, that's the secret sauce, is it?
That's the sauce. That is, you have to be able to drill down through the problem until you get to the bottom where the trouble is coming from, and figure out how to resolve the trouble or problem.
Mm-hmm.
And I can't give a recipe for that. Finding the source of things.
Yeah. Related question.
I'll give an example.
Yes, please.
For example, the strong subadditivity of entropy, which I later did with Beth Ruskay. I did that consists of two papers, well, the first of which is by myself, on all the mathematics you need to solve the problem, which was done in the second paper. And for that first paper, that came from just drilling down into a fundamental inequality, which is at the base of everything. And that's the art. Where is the source of the trouble, so to speak? And what is the essential problem that you have to solve a bigger problem?
My colleague John McGreevy asked about that. He asks, could you say a few more words about the origins of the strong subadditivity inequality? He says, in many ways, it seems to have come out of nowhere. What led you to start thinking about such questions, and what led you to your proof with Ruskay?
Well, I learned about the problem of strong subadditivity from David Ruel at IHES, and the problem was very clear, but it didn't tell where the starting point is, really. It just tells the problem is usually formulated in terms of the final answer you'd like to have. It doesn't tell you where the beginning question is. You have to drill down. And that was done in my paper on concave trace functions, which was the basis, the mathematical basis for the solution by Ruskay and myself of the final question of strong subadditivity. And so the whole art consists of being able to drill down and find the source. And that's not easy.
Yeah. Well, I mean, just going on from that, Bowen Shi asks, it has many, the theorem has many deep applications today. And he says, I assume those applications were not obvious back then in 1970s. Did you sense it would be a great thing back then? And what was the thing that really motivated you to spend time on that problem after David Ruel had brought it to your attention? Was it the beauty? Was it the simplicity? Did you look for counterexamples before you attempted the proof?
No, I didn't look for counterexamples. I believed it, but I had no idea how to solve it. Other people worked on it at that time, and there was very little in the way of applications. The problem was finding the source of things and how it related to other things. And I can't describe in detail how one does that. It just, you ask one question, and you ask another question, and you keep asking questions. And if you're lucky, you come to the source of things. If not, you start all over again.
Right. I mean, I want to
You have to believe, let me just say this, you have to believe that the question is a sensible, is an important question. Otherwise, you're wasting your time.
Sure.
And so if David Ruel asked me a question like that, I said, just take it for granted that it's an important question.
What was the work that you would say makes you especially proud?
Well, I think the solution to this ice problem, counting the number of configurations, possible configurations of hydrogen atoms in an ice or in a block of ice. This was according to rules put forward by Linus Pauling. So that's one of the other is the Lieb-Tiering inequalities, as they're called, which is important because not only did we find them, but they didn't exist. I mean, there are lots of questions out there. You say, well, I'm going to solve one or the other. But to find the question and the answer at the same time, this is the most satisfying thing. And the Lieb-Tiering inequalities, we asked the question, the fundamental question about, can you estimate the number of eigenvalues of a Schrödinger operator in terms of some integral of the potential? That question has not been clearly formulated before so precisely, and the solution given.
Yeah,
it's a bit of both.
I have another question from the audience. The style of research that you do and many of us do is sort of very bottom up, very investigator, curiosity driven, and so on. Do you have any comments? This is a question from Michael Eisenman. Do you have any comments on the long-term value of big science projects versus bottom-up driven projects?
Big science projects, you mean big machines and things like
Yeah.
that? What you mean?
I think that's what he's asking, like, huge accelerators and things like this versus, people like you sitting at a desk, sloshing some equations around and producing some fundamental insights into nature.
No, I don't. That's too hard for me. I mean, physics, if we're talking about physics, comes from lots of different directions and lots of different scales. And it's hard for one person to know all the different scales deeply enough to predict what's going to be in the forefront at any given moment. But mathematics is easier in that respect. I mean, you can more or less see what the next step is. Although sometimes somebody comes along with something original, a new direction. I believe, for example, that an example in my own life was getting on with the concavity of these matrix valued functions, matrix functions, trying to resolve them into various parts that get solved piecemeal one by one, and the whole thing put together. But this just doesn't happen terribly often.
I want to ask my last question. What did you enjoy most about being a scientist?
The chance or the opportunity to sit back and ask my own questions and think about them. And this came in my early career when I was a postdoc, and I was not very good at it. So during my postdoc years, I thought about things but didn't solve anything. Things started to fall into place when I went to IBM and worked with Schultz and Mattis and later on other people. But always it was finding the right question and having enough tools at your disposal to answer them, the right question when you do find it. And this took a long time. So I can't give any formula. Yeah.
Sure. All right. Well, Elliott, I would like to thank you again for your presentation and for your inspiring contributions to mathematics and physics. I'd like to end by congratulating you for the 2023 Kyoto Prize in Basic Science, thanking you once again for the amazing contributions you've made to mathematics and physics that have enriched the research in our community and for both professors and students.
Well, Nigel, I'd like to thank you for arranging all of this, at least locally, and you did a great job here and asked very good questions. And
Okay.
I'm honored to be able to try to answer them.
Thank you so much, and we'll keep in touch on our scientific discussions too. Everybody, that concludes our presentation this morning. I'd like to thank you all for attending and wish you well. Bye bye.